So, well, you guys just took an exam. I guess I should ask, like, how did it go? Do you have any questions? We could go through that a little bit if you would like. No, no questions on exam?
You said we could look at one, right? Could we, since like we've already taken it, could we go over one?
Yeah, we can go over it. I think we can talk about it a little bit. Yeah. Shouldn't, I mean, it would be very suspicious if like today someone submits things. So yeah, did you want to go over something? I see
Uh,
it in the chat.
yeah, the last one, 12. I think that
Last
was
one.
the
Yeah, okay.
right. Yeah, I think that's the one.
No, that's right there. Good. Yeah. Also, so I actually pre-recorded some solution videos to this exam. So I'll I'll open that up. I don't know. I'd rather open that up after the grading's finished, so you can kind of expect that around Thursday, Friday. But like after all the grading is finished, then I'll make those videos public. But we can talk about this now. So. Yeah, so yeah, something specific you want to ask, or does this make total sense and clarify things for you? Pretty much, if I see this work, like I would give this a full 7 points. So, so I can't tell unless you tell me, like, does it make sense? Do you have any further questions on this? Like the process is you take the logarithm of the function, and then you take a derivative, and then you end up solving for this k prime. So then, after you take the derivative, the next thing is you bring the 1 over k to the other side, and then replace out k with what it's defined to be, which is right here.
Is that a CO second part? That's supposed to be cosine.
Yeah, this is cosine. Yeah,
Okay.
that's cosine. This is cosine. Cosine.
Okay.
Mhm. Okay. All right.
So I have a question. The when you're going from that second that natural log x and you've kept it in the final answer.
Hmm.
Um,
Yeah.
so I guess I think there's also a way I think to find the derivative of that, but I mean it's fine if
Well,
you just leave that, or I'm a little confused.
if you uh actually, so okay. Yeah. So notice we're taking the derivative of this. This involves a product rule. So we get two terms to come out. So what you're saying, taking the derivative of the natural log, that shows up in this term. This term, you only want to take the derivative of the cosine. You want to leave the ln of x how it is.
Oh, okay. Okay, that makes sense.
Yeah, because remember, it's f prime times g. You leave the g alone, you take the derivative of the f prime. That's the first half. And then the second half, you take the derivative of g, but you leave f alone. So yeah, if you do like f prime g prime, that's very wrong.
Yeah. Okay.
Mhm. Okay, good. All right, other questions on the exam? If not, then we'll get started for today. And so the plan will be that we go up to number 4 today, and then we'll do 5, 6, and 7 tomorrow or Thursday. And that'll probably be a slightly shorter class because well, it's only 3 problems that we'll do then. Although the problems are a bit more complicated, but realistically, like if I wanted to, I could just do the whole problem set in one day. But I want to make sure at least like I'm going slowly enough that like everyone, no one is getting lost. Yeah. Okay. So, right for this week, we're talking about 2 different topics, but they're related topics. One of them is implicit differentiation, and one of them is related rates. The problem set starts off with implicit differentiation, implicit diff. And so what I want to say about it is it's a kind of differentiation where it really matters like what you're taking the derivative with respect to. So normally just been dealing with things where we just take the derivative with respect to, whatever the function is. But here we now have things like in this first problem that have multiple variables. We have x and y. And so we have this additional rule that when we see a y and we are trying to take its derivative, we instead get this thing called y prime. Now, y prime is sort of just a symbol, but you can expand that out, and it would just be with respect to whatever derivative you're actually taking. So maybe if I were to write this in a slightly different way, it's like you're taking the derivative of y, and then all you get is this thing. It's like you've done nothing to it. There's another way of thinking about it where what you're sort of saying is that y you want to treat it as like a function of x. And so then a lot of this stuff ends up looking a bit like chain rule. So, and maybe this example will show that best. So if you have like y to the n and you're taking its derivative, okay, well, normally what you would do is you would do a power rule, which would say n times y to the n. But if I now tell you that, oh, this derivative is not with respect to y, but it's with respect to some other variable like x or t, then you have this additional thing that pops out because of chain rule, because your derivative is no longer with respect to the variable y, but it's with respect to maybe like whatever y is defined in terms of. If it's y a function of x, then you'd have this y prime a function of x. You have an extra chain rule thing going on. Okay, so whenever we see, so in implicit differentiation, whenever we see things with y, we always need to remember to tack on that y prime at the very end. Okay. Yeah, and then I'll say that when we get to related rates, which shows up at number 3, well, the problem is going to be in terms of t being time. So we will have quantities that vary with respect to time, and we'll be taking the derivative of these quantities with respect to time. And so that's how related rates is very much related to this implicit differentiation topic. Okay, any questions before we start? I see someone fluttering something. Maybe that's just an internet connection thing. Okay, all right, so then, yeah, let's get started and let's do some problems. So for this, well, we start off with the left-hand side, and that's just a product rule. So you should be able to take the derivative pretty quickly. So derivative of x squared is just a 2x. We copy down the y cubed, and then we say plus, and now other half, x squared times now derivative of y cubed. So this is where that implicit differentiation rule comes into play. So normally we would say 3y squared, but since this is y, not x, I need to do a y prime after that. And so this is the derivative, this is the second half of product rule, and then the whole thing is just the derivative of the left-hand side. Okay, now the right-hand side. So notice we've got some quantity that has been cubed. So this is a power rule. We'll have a, followed by a chain rule. So we'll have the 3 times quantity, and then we square it, we decrease the power by 1. And then the next thing is I tack on the chain rule. So I take the derivative of the inner function. And so that's going to give me 2x plus 2y prime, and then the minus 1, its derivative is 0, so I'm just going to close that. Okay, and so now what we've done is we've taken the implicit derivative of the equation that we've given. Okay, the next thing is that we want to find y prime. All right, we want to find this thing. So we're going to solve for y prime. And what I want to do is I want to minimize all of the algebraics that, like, I don't want to write a whole bunch of stuff when I'm doing this. So a lot of the algebra I'm going to end up doing mentally, but I'm going to try to talk you through it. So if I look at what terms have a y prime, I see these two. Okay, I'm highlighting this term, but that's because, like, notice that these two terms get multiplied by this 3 times quantity squared. So just imagine mentally that this is getting distributed. So we're going to do the distribution in our heads, and then we're going to subtract over this 2y prime. That way, we start our writing by saying y prime, and then put a big set of parentheses. So I'm going to move the terms with the y prime, all of them, to the left-hand side, and then I'm going to move the terms without the y prime, all of them, to the right-hand side. And the terms that have y prime on the left-hand side, I'm going to factor that y prime out right away. So this, the first term I'm going to write down is going to be this, and I can rewrite that 3. There's a multiplication there. Rewrite that 3 in the front because that's the normal way that we would write things. So 3x squared y squared for the first, the guy in blue. And now for the second guy in blue, we would have a subtraction because we subtracted over, and we would distribute. So 2 times 3 will be a 6, and we have a y, and then we've got that quantity that's squared. X squared plus y squared minus 1 all squared, and we close the big set of parentheses. Okay. And now the terms that don't have the y prime, we move them to the right-hand side. So this term, this 2x, stays. And this term, 2xy cubed, that's going to move. So then we would have a negative in front of that. Now distribute, and let's write down what we get. We'll get a 6x quantity squared, minus 1. And then we minus this first guy in green, minus 2xy cubed. Okay, so I reduced a lot of algebra that I would otherwise have to write, but this is something that you should just be able to do mentally. Did everyone follow getting from this point to this point? Any questions? No questions? Okay. Then finally, we write down our answer. So we have all of this that's being multiplied by y prime. All we have to do is we divide over. So that's just going to be me copying down the right-hand side first. 6x quantity squared minus 2x y cubed. And then lastly, we divide over the 3x squared y squared minus 6y, and then quantity squared. Okay. And so that is our answer to this. So I can go ahead and box this guy. All right. So that was part A for this problem. Now let's go and think about part B. So notice it wants us to create the equation of a tangent line at this point. And the equation it's giving us is the same equation as above. So really, all we need to do is evaluate this derivative at this point. So remember how the process of doing tangent line. We need a slope and we need a point on the line. One thing that you should probably check is that this point does indeed lie on this line. So just like plug it in and you'll see like you get 1 = 1. So yeah, this point lies on this curve that's defined. And if you want to see if this is actually a curve, you can just graph this, type this into Desmos and just it'll graph it for you. Yeah, so we need a point, we need a slope, we need a point, we have a point. Slope is going to be given by this derivative that we just calculated in part A. So all we do is we take our y prime function, we evaluate this at the point 1, 1. Okay, so this is just a calculation. Let's see, 6, 1, this guy is going to be 1, so we get 6 minus, and then 2 over 3 minus 6. So if the numbers weren't x = 1, y = 1, this would be a much more bothersome calculation. Here we're given an easier situation. Okay, so we figured out m, and we have the point, and we just combine these two pieces together. Y minus y naught is equal to m x minus x naught. There we go. That is the answer for 1b. Now for number 2, there's 4 parts, and each of them is just practicing implicit differentiation, practicing this process, and they're not too bad. So yeah. Well, just go through it. So for 2a, tangent, you should remember that its derivative is secant squared. So you would write this down, and then you remember, well, if we're taking the derivative with respect to x, as this is saying, well, this y is something else, and so we have a y prime at the end. And so that ends up being the implicit derivative of the left-hand side. The right-hand side, well, it's just power rule. We're going to have 3 that pops out, and then we decrease the power by 1, so we get that. Okay. And then lastly, we need to solve for y prime to answer our problem. Well, here solving is pretty easy. We just need to divide that secant squared over. But I will ask this. So who knows what I get? What do I get when I divide secant squared over? In other words, what is that?
Is it cosine?
It's cosine. Yeah. Yeah. And so it would be a lot better if we just phrased our answer in terms of cosine instead of a secant in the denominator. This is the kind of thing that you kind of one would expect that you immediately recognize that. So yeah, instead of phrasing this as secant squared in the denominator, I'm going to bring that secant squared up as a cosine. So we'll get a cosine squared in the top. Okay. And so I can write it like that, and I can box this answer. Oh no. There we go. Yeah, I mean, if you wanted to, you could put that in. You could put like 3x squared over 10 secant squared, but I don't know. That doesn't look as nice to me. So whatever. Okay. Well, b, that's looks very easy. Derivative of x cubed. Everyone should know. This xy, everyone should immediately think of this as a product rule and take its derivative would be y plus xy prime. And then this, so yeah, this again, this is the implicit derivative. So you get a 3y squared y prime. And then that is the left-hand side. The right-hand side, derivative of 10, well, that's just going to be 0. All right. So now we took that implicit derivative. Next, we solve for y prime. Okay, well, at least here we have terms that have it and terms that don't have it. So these two terms have y prime, and these two terms do not. So we're going to move the terms that are in green over. We're going to group the terms that are in blue together. And so we'll have x plus 3y squared is equal to minus 3x squared minus y. Okay. Everybody follow what I did there? No questions? Okay. And then lastly, we divide the stuff that is in the parentheses. So we'll get y prime is equal to minus 3x squared over y, or minus y, over x plus 3y squared, which we can then box, because that's the answer. Okay. And now for C. All right, so first term is a product rule. Second term, well, we'll talk about that. Okay, so 2xy plus x squared y prime, right? That's the derivative of the first term. For the second term, well, the derivative of an exponential, as we know, is the exponential itself. So we would write this, but because this is y instead of x, we know that like there's sort of a chain rule that happens. The implicit derivative tells us that there's a y prime that comes out. Okay, so this is actually the derivative of that e to the y. And now the left-hand side, well, we get just a 1. Right? Derivative coming from the derivative of x. The plus 1 goes away, it becomes 0. So we don't need to do anything, say anything about that. All right, and again, we do the whole grouping thing. So these two terms, they both have y prime, so we just would get x squared minus e to the y on the left, and then we would subtract over this minus this 2xy, we would subtract to the other side. So we would get equals 1 minus 2xy. And then lastly, we divide. So we'll get 1 minus 2xy over x squared minus e to the y. And we can box that. Okay. Move that down a bit. There we go. All right. And part D is maybe the harder of all of these, but still not that hard. So it's harder because you have a chain rule that is going to involve the product rule, right? You can kind of see that from here. So derivative of cosine is the first thing that you do. And you should remember the derivative of cosine is negative sine. And then, well, you need to do derivative of the inner function. So that's going to end up involving a product rule. So end up taking the derivative of this xy. Well, that's going to be y plus xy prime. And so that's the left-hand side. The right-hand side, just the derivative of x squared, so that's just going to be 2x. And now we need to solve for y prime. So, well, notice that this term, we're going to need to distribute the minus sine xy to both of these terms. And this one will stay, the other guy will move. And so we're going to have a y prime times a negative, I can put the x in front actually, that's sort of the more normal way you do that. So minus x sine xy, yeah, is equal to 2x. And then when I distribute, I'm gonna get something negative, so then I need to add. So we're gonna have a plus, and then this will be a y sine xy. And so that is, yeah, we're still solving. We just now divide this over. So we get 2x plus y sine xy all over x sine xy. Okay, there we go. And so that's our answer.
Wait, why did you add the y sine xy on the end?
Well, because when I distribute at this stage, right? When I distribute, this is gonna have a negative in front of it. I'm gonna get a minus y sine xy, and then I need to move that quantity to the other side. The way you move that is you flip the sign, you add it.
Oh, that makes sense. I got it. Thanks.
Yeah. Okay, good. Yeah. All right, so that's 1 and 2. Now we start doing some problems that have related rates. Okay, so well, this is where I say that like these types of problems are a bit hard to teach because the way that they end up working is a bit like puzzle solving kind of. It's sometimes the way of thinking about these is a little bit non-linear. You're just like grabbing things and putting things together. But I'll try to give like an idea as to how you normally approach it. And also I'll say that so I have some videos that I recorded from the previous semester, and my YouTube channel now, it links to those videos, so you should be able to see them. So if you want to see like additional problems that involve related rates, just to like, I don't know, get some extra experience, extra practice, you can look at those videos and you'll get, you know, more of an idea of how related rates works. It's a topic that I guess is easy to be confused by until you sort of try out enough problems where you kind of get the hang of like how it works, I guess. But yeah, so related rates. So what I want to say about it is, well, what you do with it is you usually, well, I usually start by drawing a picture, but I'm not going to write that. But yeah, it's a good idea to draw a picture. And the first thing that you want to do to such a problem is you want an equation that describes the situation for all time. So your problem, like these related rate problems, involve some sort of a system that evolves over time. Like quantities are changing over time, and finding a related rate is just finding how does this specific quantity change with respect to time. And the idea is that the quantities are related to each other in some way, and you have an equation that describes their relationship. And so you want that relationship to be completely encoded inside a single equation. Then, so that's why I'm saying for all time. Then what you do, where's my cursor? Then what you do is you take that the time derivative. Take the time derivative, which is an implicit derivative. Namely, it is a d dt of that equation. And so at this point now, you would have an equation that describes the way that quantities are changing with respect to one another. It's a relationship on how the rates are actually related, hence the name of this section. And then step 3 is that you plug in all your information. And then at this point you would hopefully you would have all the information that you need that you can just get the answer. So yeah, sometimes what happens is that there's a relationship that you just need to realize is there in the problem. Like there's like an equation that you just didn't find in the problem, and then once you have that equation, it relates these two quantities, and then that just simplifies everything down, and you just plug right in and you'll get your answer. So usually with these problems, it's just in this way. So long as you get all your data, you can then plug your data in to that equation from that is like that derived equation. You can then plug it into that equation, and then you'll just get the quantity that you're looking for, the specific related rate that you're looking for. Okay. Well, you'll understand what I mean when you like do enough problems. You'll see that this is kind of like the overall the global idea of how these things work. But yeah, so let's see. Number 3. In this case, yeah, we should draw a picture. So there's a person that's traveling west, and then there's a person that's traveling north. And this is going to end up being a triangle. And once we get a triangle, the first thing I do is I call this X, I call this Y, I call this Z, just to match up with the coordinate axes. And we're gonna have that once you have a triangle, and this is like the most common type of related rates problem is when you're dealing with a triangle. So in this case, it's a triangle where the hypotenuse is changing. Just I'll say that. But so right, what is the equation that describes how these three quantities are related to one another? Well, the thing that you know is Pythagorean theorem. So you should immediately say x squared plus y squared equals z squared. Okay, that's how these quantities are related to one another. And then you would take the time derivative of this equation. You do a d dt, and then that's going to give you a 2x x prime plus 2y y prime is equal to 2z z prime, where here my prime means it's a derivative with respect to time. It's a d dt. So a lot of the lecturers, what they'll do is they'll write this out explicitly. They'll say dx dt, dy dt, dz dt. Like, but the thing is that uses more time to write. So I would rather just use the prime notation, and always in the back of my mind, I'm thinking, okay, prime is actually a derivative with respect to time. And it's pretty clear from context that that's the case. I guess, yeah, only when you're like really trying to emphasize what the derivative is with respect to, would you go like from the prime notation to actually explicitly spelling out, oh, this is d z dt. And usually that's only necessary if you have multiple variables, like, but you'll get to that if you like take Calc 3, for example. Anyway, right. Then from this stage, well, I need more quantities, so I need to read the rest of the problem. So the person that's traveling westward, he's traveling at a rate of 3 miles per hour. So that means x prime is 3 miles per hour, and y prime is traveling 4 miles per hour. And the question is asking, at what rate is the distance between two people changing 1 hour after? Okay, so that is actually asking us to find z prime, and it's saying when what's changing 1 hour after they start walking. So when the specific moment in time that we're looking for is t equals 1 hour. So this is where when I now need to explain, like, I have this terminology of a moving or a dynamic picture versus a static picture. So what I've drawn here is I'm thinking of it as a moving picture, a dynamic picture. Like this is actually, imagine this is an animation that is like kind of changing. So because the quantities x, y, and z, they're all changing actually over time. But in this problem, like this z prime, it's specifying it's at the time 1 hour. So we're looking at a specific snapshot in time, and in that snapshot, what is the configuration of our system? So that the static picture is going to have, and then in this case, the numbers are really easy. So you start like at this point, and you travel 3 miles per hour for 1 hour, you're gonna be 3 miles apart away from this starting point, and the other guy is going to be 4 miles away. And then, well, hopefully you know about the Pythagorean triple, 3, 4, 5. Right? If you don't know, then you have to plug into the Pythagorean formula theorem. It's called a theorem, but it's just a formula. It's kind of I don't like that. Okay, yeah. So 3, 4, 5. Okay. Great. Right. So this is a bunch of data, and now that we have all this data, we can plug in. We have x equals 3, y equals 4, z equals 5, x prime is 3, and y prime is 4. So we're looking for z prime. So we have 5 pieces of data. We're trying to find the 6th. We have everything that we need to solve this. Actually, also, I would say, like, I forgot to say this, but yeah, I would cancel all those 2's up front, so because it's just unnecessary. All right, so let's see. If I plug in 3 times 3 plus 4 times 4 equals z is 5, and we're looking for the z prime. Okay, well, 3 squared plus 4 squared is going to be 5 squared. Is going to be 25. So I get 25 is equal to 5 z prime. Therefore, z prime is 5. And I should put units since this problem has units. And so these units are miles per hour. So I'll put miles per hour, and then I'm done. Okay, so I can try to box this hopefully. Good. All right. So hopefully this process made some sense. Hopefully you're able to follow along. I think in this case, like I wasn't so nonlinear about it. Usually when you're like completely looking at a problem that you haven't done before, like you might need to jump around a little bit, and though the working out is a bit nonlinear. Yeah, okay, so right. Now for number 4, well, we have a ladder and it's leaning against the wall, so let's just draw that. That is a triangle again. But this time the length of that triangle, the hypotenuse, is fixed, right? The ladder, you don't expect the ladder to suddenly grow or shrink in size, so that's going to be fixed. And the top of the ladder we know is sliding down. I should also put x and y here. So the top of the ladder is sliding down, which means that this endpoint should be going to the left. Okay. And well, since this is a triangle, a right triangle, we want to immediately write down the equation that describes the situation. X squared plus y squared is equal to 13 squared. But then when I take that derivative, I'm going to get 2x x prime plus 2y y prime is equal to 0. So this is where it is slightly different from the first problem. So In the first problem, our z was changing. Here, our z does not change. Okay. Again, the 2's are redundant here, so we can just divide the whole equation by 2. Those will cancel. Okay. Okay, so now let's read the rest of the problem. The top is slipping down at a rate of 1.25 feet per second. Okay, so y prime is equal to 1.25 feet per second. I know that I'm going to want to I'm gonna want to turn that into a fraction. So I'm going to say that's 5/4 feet per second. Okay. So who is unhappy with what I've just done? I've just done something wrong, by the way. Okay. So if you're keen, if you're paying attention, you'll notice this thing, this quantity y, right? The ladder is falling down. Y is decreasing in size. Therefore, this statement is wrong. It's not 5/4. It's negative 5/4. That negative is important. Okay, so this is the kind of thing that you need to pay attention to when you're dealing with these problems. That negative is, if you didn't have that there, the mistake is going to propagate to the rest of the problem, and then you're going to have something incorrect as your answer. And you might be able to cleverly just like take the absolute value and you'll get something, but you should be a bit more cautious about what you're doing. So this kind of mistake I've seen on exams, and yeah, I take points off for that. I think most people will take points off for that. Common mistake, just be aware of it, make sure you don't make that mistake. Okay. There's ways to also like check your answer to make sure to just like sort of sanity check your answer, make sure like, oh, if you get a negative quantity when you expect the quantity to actually be increasing, well, that means that you probably made a mistake somewhere. Try to find where that mistake is. Okay, right, so y prime I translated. X prime, well, actually, how fast will the bottom, okay, so we're looking for x prime. Yeah, find, if we translate that last part, it says find x prime when the top is 12 feet. So when y equals 12 feet. Okay, right. So, all right, so here I have the moving picture. What is the static picture look like? Well, let's draw it. So we still have 13. If we are fixed at the point in time when the height is 12, okay, so we have like that. Well, this is the other Pythagorean triple that maybe you can recall, and 5, 12, 13 is the way it goes. So you got 13 and 12, so the other guy has to be 5. If you didn't know 5, 12, 13 as the other common Pythagorean triple, then what you would have to do is you'd have to use the Pythagorean formula to calculate it. And so then the calculation that you would do is the square root of 13 squared minus 12 squared, which, well, it's just the square root of 169 minus 144, which is the square root of 25, which is 5. So yes, this is correct. Okay. Right, so now we have a bunch of data and we can plug in, I think. We have x is 5, we have y is 12, we have y prime, and we're looking for x prime. So we can plug everything that we need into this equation. 5x prime plus y, where's y? 12. Y is 12, y prime is negative 5/4. And we're setting that equal to 0. Okay, so when we solve this, we're gonna get minus 15. Okay, so 15 divided by 5 is going to be 3. And then, of course, we have to check units. So feet per second is what the problem says. Well, what the problem is in terms of. So there we go. I can now box that. Okay. I don't like it. There we go. Okay. So, right. I don't want to go any further than this. So that way we'll have like enough to talk about for next time. So are there any questions If not, then we can end here. No questions? Okay, then I'll stop recording.